Okay, so now we have a field which is not constant, but it's still just in one dimension, and it's got some value that changes here. So the idea is that the E field points to the right for positive x and grows in strength as you move away from origin. So again, if I want to set this up, inside my integral, I'm going to have that E dot dl. And so that would be the EX dx plus EY dy plus some EZ dz. But since I only have one dimension, I only really care about this part. And so my potential is going to be minus the integral of EX dx from some reference position out to some value x. And again, our textbook will sometimes use a x prime just to say that's my integral variable versus my actual position variable later. And just plugging in my particular value here. And then solving this integral. I've got a minus, I'm going to have a 1/2 kx prime squared, evaluated from some reference position up to some x position. And so my potential is going to be 1/2 or minus 1/2 kx squared plus some
Is that a 12?
v naught.
Oh, no, that's a 2. The x squared is a 2.
Yeah, it was an x prime squared. That's where. And so again, we can put this last part as whatever my zero potential is. Okay? As my constant of integration there. And just to verify, I could do the gradient of this potential, in which case my EX would have to be minus the partial of that with respect to x, minus the partial with respect to x of a minus 1/2 kx squared plus v naught. Can't forget that part, because we'll see what happens to it here. And when I do that derivative, well, my minus and my minus are going to cancel each other out. And then I've got 1/2 k, but the derivative of x squared is 2x. And the derivative of a constant gives me nothing. So I get kx. So again, that EX is the same thing as what I had up here. So it worked. Okay? So we can, if we have the potential, we can find the electric field, but if we have the electric field, we can find the potential.
Okay, I know you have the 2x in the parentheses at the bottom. How did you get the 2?
Because when you integrate, or when you take the derivative of x squared, you get 2x.
Okay.
Okay? Okay, I'm gonna, in this video, go ahead and keep going because I'm gonna do another example. And again, these are from the ones that were suggested by my ChatGPT. And so we're gonna go ahead and do the first one here. So again, I want to write out my E.dl for this particular case. And so it's going to be 2x dx plus 3y squared dy. That's what goes inside the integral. And so because this is two different things, we can split this into two integrals minus the integral of 2x dx and minus the integral of 3y squared dy. And when I do this one, I'm going to have a minus x squared, because the integral of x dx is 1/2 x squared. And then when I do this one, I'm going to get y cubed. Both of these have constants of integration, but I can combine that into just a single constant of integration.
What if the y was already squared though? What does that happen to?
So that because you've got y squared dy, that's 1/3 y cubed.
Oh.
And so that's why when they had the 3 out front, it became the y cubed. Okay? And so we've got a potential function that is minus x squared minus y cubed plus some reference potential. I'm going to do one more in the same video, just to again show you another one using rectangular coordinates. And this is a mixed function field.
Is this something similar to the one we just did?
Yep. So again, you want to start by looking at what is E.dl for this case. And so I'm going to have a y squared dx plus 2xy dy. And I've got to do the integrals here. And so when I break this down, I'm going to have the integral of y squared dx and the integral of 2xy dy. Well, since I'm integrating this one just with respect to x, and x and y are independent, this is y squared, the integral of dx. Keeps giving me these extra lines. And again, looking at this one, I can pull the 2x out front, and I've got the integral of y dy. This is going to give me minus y squared x. This one is going to give me the integral of y dy is 1/2 y squared. And of course, I've got constants of integration. Well, this term is really minus x y squared. And this term is also minus x y squared. And you might be tempted that there's a factor of 2 in there because I had it from both of them. But what really happens here when we're doing this is what we really need is the union, not the addition. So what do I mean by this? It's best to actually think about this in terms of going the other direction. So if my answer was minus 2xy dy, 2xy squared, not dy, minus 2xy squared plus a constant, then when I did my electric field as minus the gradient of the potential, I would have Ex would be minus the partial with respect to x of 2xy squared plus c, which would give me, there's a minus sign there too, which would give me plus 2y squared. And my EY would be minus the partial with respect to y of this function, which would give me plus 4xy. But that's not the electric field I started with. If it's the union, then when I do this, I can do my partial derivatives and these are the correct ones. So because our gradient has 3 terms with the partial derivative, when I'm doing my integrals, if my integrals give me things which are in common, instead of it being just a straight adding of those things, it's the union of those things. So minus xy squared, yeah, that came out from both of those terms. So that must be one of the terms in the potential. And then I've got some constant of integration. Okay? Now I'm going to stop this video here since these are ones doing it in the x coordinate systems, and there's going to be some other videos with some examples using cylindrical and spherical coordinates.